In this video, we will solve combined loading problems. Well, in this problem, we have a drill and a torque, 20 Newton meters, and the force, 150 Newton with a given angle, is acting. Determine the stress state in point B on this section AA of drill bit. Okay. So this is my drill bit, and we are interested in this point B. Well, let's cut in section AA, and in this section, well, the possible loads are a normal, shear, a torque, and the bending moment. Okay, we have to find these internal loadings. Well, we start with the equilibrium equations. First in the Fx, in the x direction, we have n, and we have the vertical component of 150, that's 4/5 times 150, n minus this value, that's 120, is equal 0, n is equal to 120 newtons. Now the y direction, we have minus shear force and plus the vertical component of the acting 150, that would make 90, and my shear force in the y direction is 90. Now sigma mx is equal to 0. That's the torsion around the x-axis. Here we have the torque at the tip and the torque which is applied, so we can easily find out that T is equal to 20 Newton meters. Now bending around MZ. Z is the axis perpendicular to the screen, Z. As you see, this is my X, and that's my Y, and bending around Z is like this. Okay, so as you see, we have our MZ, and around the Z-axis, component of 150, the horizontal component is 120 Newton, that is this one, okay, well, which tries to rotate in the same direction, as you see, as MZ, also positive, and we have another component that is this component that is 90 newtons and is trying to rotate in the opposite direction. It has a negative sign, so if you solve for MZ, you find that MZ is 21 Newton meter. Let's calculate the area, the moment of inertia around Z, and the polar moment of inertia for torsion. So we need this for stress calculations. Okay, let's start with normal stresses. Normal stresses are caused by normal forces and bending moments. Here we have a normal force which is 120, compression minus 120, and that is my area, and this is the force caused by normal force. What about MZ? As you see, well, when you bend around the Z-axis, well, in the section of the drill, well, a stress distribution will be caused. So the stress in the neutral axis will be 0, and on the top and the lower end, we will have maximum and minimum values. So in this problem, we are interested in point B, and my point B is exactly on the neutral axis. So the y value, which is the distance from the neutral axis, is 0, and so we do not have any normal stresses caused by bending. So as a result, well, only normal forces cause a compressive stress value which is uniformly distributed in the section. Next, shear stresses. It may be caused due to shear forces and due to torsion. So let's start with the shear forces. I have a shear force over here, and as you see, the shear force is 90 newtons. My point B is over here. The stress distribution looks like this. My point B lies on the axis where the tau value is maximum. So you can use this formula and calculate V and Q as we did in the previous slide, and IT and the T, and find this value. But I also remind you, for simple section like a circular section, you can use for the tau max value 4/3 V over A. A is your area, which is pi r square, and V is your 90 newtons and 4/3. And if you do this calculation, you will end up with the same result. Okay, this is the shear force due to shear stress due to the shear force 90 newtons. Then we have the torsion. Well, the torsion is 20 Newton meter. My radius, polar moment of inertia, and this is the shear force due to torsion. As you see, the torsion is maximum all over on the surface, 0 in the middle. My point B lies on the surface, and it will have this maximum value. Okay, I have 101.89 as a tau due to torque, and as you see over here, my V, that means my shear stress, was in the opposite direction, so that's 101, and that one is 1.528. So if you make superpositions, these two stresses are the same type, but in the opposite direction. Considering their signs, my total shear stress is 100. So in point B, in summary, I have a sigma value of minus 1.5 and a tau value 100 megapascals. You can show this on a volume element. So your sigma is compression minus 1.53, and your tau is 100 megapascals. Next problem. Well, we are applying 50 pounds, and the section I'm interested is AA. I'm especially interested in point A in this section. It's a pipe. My point A lies over here. You see This is my z-axis, that one is my y-axis, and the x-axis is perpendicular to the screen. Okay, so we cut in AA and write down all possible forces, two components of shear. There may be a normal force, and there may be two bendings and one torsion. Now we use our 6 equilibriums. The first one is actually sigma f x equal to 0, but since that 50 does not have any component in the x direction, n can be written as 0, and if you write Fy equals to 0, well, Fy this force and the vertical component equals to 0, you find Fy. In the Z direction, you have this force and this force. If you write these down, you find the forces. So with the three forces are now found. Next step, we calculate the moments. The first one is sigma mx. Mx is the longitudinal axis, so a moment around this axis is actually a torsion. So we have my torque, and the torque which is created by this 50 is the vertical component times the moment arm. So the vertical component times the moment arm. So you find the torque, and for bending, my. Y is this axis. So bending around this axis is caused by this component, and as you see, you have this moment arm times component. You see the signs we have taken are this. If you take this as positive, so like this, the other one is in the opposite direction. That's why I take the minus. So I find the my value and mz. Mz, let me clean all this stuff. And mz is bending around this axis. So it tries to bend the pipe like this. And this is my positive mz. And 50, this component, times 10, also tries to bend in the same direction. That's 50. So 50 times sine 60 times the moment arm 10, you can find that mx is minus 433. As a result, we have our internal loads and internal forces acting in section AA. But as you see, the torque I have taken in this direction is actually in the opposite, and as you see, the bending moment around Z is also in the opposite direction, not in the direction I have taken. Well, here are my internal forces and moments. Now we begin to calculate the stresses in point A. Well, first the normal stresses. The normal stresses may be caused by normal stress and by bending moment. Here we do not have any normal stress, only bending moments around Z and Y. Well, if this is your section, well, your Z lies like this and your Y like this. Well, if you have a bending around Z, your stress distribution will be looking like this. In the middle, on the neutral axis, you will have 0 on the top, and on the lower end, you will have your maximum and minimums. So this distance is the radius, which is 0.75. So let's begin with MZ. MZ, where is this formula? We have this formula. Y is 0.75. This is my MZ. This is the Y value, and this is the IZ value, which I have already calculated. And the result is 605 at this top, 605. What about the Y? Well, when you apply bending around Y, well, your stress distribution will look like this. And on the axis, we have zero stress, and on the right and left ends, we have maximum. But my point A is directly on the neutral axis, so its distance from the axis is 0, and we do not have any stress due to My. So, as a result, the stresses developed due to the bending moments and the normal forces, which are effective in creating a normal stress, is only 605. My has no effect and does not exist only due to Mz. Now the shear stresses. First, due to torsion, we know this formula. Well, when you apply a torsion, as you see, well, the torsion is in this direction. As you see, the formula gives you 362, and the torque is and this stress is everywhere on the surface, also on in my point A. Next, due to shear, we have our section and we have two shear forces. The first one is Vy, which is acting as you see in this direction, Vy. The other one is Vz acting in this direction. If you consider only Vy, your shear stress distribution will be looking like this. Your maximum is in the middle on the surface, it's 0, and my point A is also on the surface. So you see the stress due to Vy is equal to 0. What about this one? Well, in this case, I can use this formula. Well, I have already calculated the Q in the previous slide, and this is my V, and these are the Iy and T values. But we already know that there is a simpler formulation of the tau max. If you have a circular section, you can take V and divide it by the area and find the same value by using this simple formula. Well, here we have everything. My normal stress, my shear stress is due to torsion and due to the shear force in the Z direction. I have to find the total shear stress. How do I find it? So this is my section, my point A. Well, as you see, the torsion gives you stress in the negative direction, and this one gives you one in the positive direction. So minus 362 plus 35 gives you minus 327. Well, the question was, what is the stress rate in point A? The result is in point A, normal stress of 605 psi and a shear stress of minus 327 is okay. In this video, we solved two combined loading problems. We made the stress analysis and found the stress states for the asked points. Thank you for listening.